Welcome to the deep dive. Today, we're going to shrink down, like way down to the microscopic world of precision actuation.
Oh, I love this stuff.
Yeah, they're everywhere. I mean, they're behind like crazy innovations, especially, stuff like microdosing medicine. You,
Yeah.
you actually share this really cool technical checklist uh, about microdosing extruders.
Yeah,
And
yeah.
that got me thinking, like, we got to dive deeper into how these precise, tiny movements are like literally shaping the future of uh, biomedical devices.
Yeah, it's incredible. It's such a fascinating area because, just a few decades ago, we couldn't even fathom controlling motion at these scales. Like, it was just unimaginable.
So, okay, before we like shrink ourselves down like literally to the size of like a molecule,
Yeah.
can we start with like the basics?
Sure. Yeah.
What even is actuation? Like, I know things move, obviously, but what's the science behind, making that movement happen, like on purpose?
You're right. It's easy to just kind of take movement for granted. But actuation, at its core, is basically creating or controlling movement in any kind of mechanism. You can think of it as the force, the driving force behind anything that changes position.
Okay.
Whether it's a robotic arm, the lens in your camera, or even, your own muscles.
So it's like the oomph that makes stuff actually do stuff.
Precisely. Yeah, it's the get up and go. And then when you add precision into the mix, then we're talking about controlling that movement with extreme accuracy. And, even the tiniest error can have a huge impact, especially in fields like, microrobotics or delivering those precise doses of medication.
And I bet that's where things get like really complex. Is it all just like super tiny gears and motors?
It's actually a lot more diverse than you might think. There are 8 main types of precision actuation systems, each with its own kind of strengths and quirks. And not all of them rely on those traditional mechanics that you're thinking of.
Okay, I'm officially intrigued. Let's meet these star players of the precision world.
Mm.
First up on the list, piezoelectric actuators.
Yes.
What makes them so special?
Piezoelectrics, these are some of my favorites, actually. They harness this really unique phenomenon called, well, it's called a piezoelectric effect. And basically what it means is certain materials like quartz or some specialized ceramics, they actually change shape when you apply an electric field to them.
So it's like they're flexing their muscles, but with electricity instead of like protein shakes.
That's a great way to put it. It's literally flexing with electricity, and this flexing action can be controlled at the nanometer scale. We're talking like 1,000 times thinner than a human hair.
Wow, that's mind-blowing. Where would you even use something that precise?
I mean, think about adjusting the tiny mirrors in a high-powered laser or focusing the lens in a really cutting-edge microscope. Piezoelectric actuators are also essential for inkjet printers and even manipulating those tiny, tiny samples in, advanced scientific instruments.
So they're like the micromanagers of the technology world, just making sure everything's perfectly aligned.
Exactly. But like any technology, they have their limitations, right? Their
Yeah.
range of motion tends to be relatively small, and they sometimes need those higher voltages to operate.
Okay, so tiny but mighty and maybe a little bit power hungry.
A little bit, yeah.
Next on the list, servo motors. I kind of associate those with like heavy machinery, not, delicate movements.
I get that. That's a common misconception. Servo motors are really all about precise control of motion, not necessarily like raw power.
Okay.
So when you combine them with high-resolution encoders, which kind of act like their internal GPS system, you get incredibly smooth and accurate movements.
So it's like they have a built-in sense of direction.
Exactly, yeah. They know where they are, where they need to go. And this makes them great in applications where you need to constantly adjust position and speed. So like robotics, automated manufacturing, even controlling those camera gimbals for super smooth video.
Yeah, I'm starting to see a pattern here. Precision is all about like feedback and constant adjustments.
Yeah, it's all about the feedback.
But do servo motors have any like downsides?
Yeah, I mean, they can be complex to control. They often require sophisticated electronics to manage their movements. And their precision is also, very reliant on the accuracy of that feedback system. If an encoder's faulty, throws everything off.
Got it. From smooth operators to, kind of a click, click, click approach. We have step motors next. What's their specialty?
Step motors, yeah. They are the masters of precise incremental movements. Imagine like dividing a full rotation into hundreds or even thousands of tiny steps. That's what these motors do best.
So they're like the digital clocks of the movement world,
Mhm.
always moving in these like distinct measurable steps.
That's a great analogy. And this ability to move in those precise increments makes them perfect for applications where repeatability is super crucial, like in 3D printers, CNC machines, even some medical devices that need to dispense precise doses of medication.
I'm starting to see how each of these actuators kind of fits into a specific niche, you know.
Yeah, totally. Yeah.
What about, are there any limitations of step motors?
Yeah. So their motion can be a bit jerky compared to servo motors, especially at low speeds.
Okay.
They can also lose accuracy if they're overloaded or forced to move too quickly.
Interesting. So precision is like this balancing act between speed, power, and accuracy.
It really is, yeah.
Now let's zoom into like the fast-paced world of voice coil actuators or VCAs. What makes these guys stand out?
VCAs, yeah. These are like the sprinters of the actuation world. They're known for their incredibly fast and precise linear movements.
Okay.
They use the interaction between a magnetic field and an electric current to generate force. That's where they get their speed from.
Okay, so we're talking electromagnetism in action.
Precisely.
Okay.
And this principle allows for really fine control over like short distances, making them perfect for applications that demand those rapid responses.
Okay,
So like high-end audio speakers, the focusing mechanisms in cameras.
got it. So if I need something to move quickly but also accurately, VCAs are the way to go.
Exactly. But there's a trade-off. Their stroke length, or the distance they can travel, is pretty short compared to some of the other actuators.
Makes sense. Now for the heavy lifters, hydraulic and pneumatic actuators, I mean,
Yeah.
those are the big guys.
These are the powerhouses. Hydraulic actuators use pressurized fluids, while pneumatic ones use compressed air.
Okay.
Both are capable of generating enormous force, so they're perfect for moving those heavy loads.
I can see how those would be, essential for construction equipment or industrial robots, but can they even be precise?
Absolutely. Yeah, with those advanced control systems, they can achieve surprisingly high levels of precision, especially in applications that need both strength and accuracy.
Okay.
So like controlling the movements of an excavator arm or, precisely positioning those heavy components in a factory.
So it's not just brute force, there's finesse too.
Exactly. There's a delicate touch to them. However, maintaining that precision can be tricky because of things like pressure fluctuations or potential leaks.
Right.
These systems need that careful monitoring and maintenance to make sure they're performing reliably.
Got it. Next on our list are direct drive motors, which sound, delightfully straightforward.
Yeah.
What's their, philosophy?
Direct drive motors are all about simplicity and efficiency. They connect directly to the load they're moving, which eliminates the need for gears, belts, or any other transmission components that can introduce errors or wear and tear.
So it's a pure, unfiltered connection between the motor and the movement.
Exactly. And this direct connection results in some exceptional precision, smooth motion, incredible responsiveness. They're often used in high-performance robotics, precision manufacturing, even advanced prosthetics.
It's all about cutting out the middleman for maximum precision.
You got it.
Are there any downsides to this, direct approach?
Well, they can be more expensive than other motor types, and managing their temperature can be a bit of a challenge, especially, in high-power applications. But often, their performance benefits outweigh these considerations.
Okay, now we're going even smaller. Tell me about electrostatic actuators.
Oh, yeah. These are the true micromachines of the actuation world, often found in what we call MEMS, micro-electromechanical systems. They operate on the principle of electrostatic forces, like static cling, and it creates those incredibly tiny, precise movements.
Okay, so we're talking about harnessing the power of static electricity to actually move things.
Precisely. And because those forces are so tiny, electrostatic actuators are perfect for manipulating microscopic objects like, the tiny mirrors in a projector or the valves in microfluidic devices.
But they're like the ultimate micro movers.
Yeah, but their force output is quite limited, so they're not suitable for moving anything heavy. They're all about precision, not power.
Okay. Last but not least, we've got magnetic levitation actuators. Maglev sounds incredibly futuristic.
Oh, it is. Maglev actuators are all about frictionless motion. smooth motion. They use magnetic fields to suspend and move objects without any physical contact.
Whoa.
And that results in unparalleled precision and virtually silent operation.
So it's like they're gliding on air.
Exactly. This tech is already being used in those high-speed maglev trains, but it also has applications in precision manufacturing and robotics where friction and noise can be major obstacles.
I'm starting to see how this could revolutionize, like, all sorts of industries.
Totally.
But I imagine a technology this advanced comes with its own set of challenges, right?
Yeah, you're right. Maglev actuators can be complex to control, and they require sophisticated electronics to manage those magnetic fields. They also tend to be quite expensive compared to other actuation technologies.
Well, it seems like precision often comes with a price tag.
It often does, yeah.
So we've met all 8 of our actuation all-stars, each with its own, like, strengths and weaknesses. But you mentioned earlier that precise control is, like, key no matter which actuator you're using. What does that look like in practice?
You can think of it like conducting an orchestra. You have all these talented musicians, each capable of producing beautiful sounds, but without a conductor to guide them, it's just chaos. Similarly, even the most capable actuators need precise feedback and control systems to function effectively.
So it's all about communication and coordination.
Exactly. Sensors play a crucial role, constantly monitoring the position and movement of the actuator and feeding that information back to a controller. The controller then makes adjustments, ensuring the actuator is moving exactly as intended, correcting for any errors or disturbances.
It's amazing how these systems work in harmony to achieve those, like, incredible results.
Yeah.
Now let's shift our focus to the world of biomedical devices where precision takes on, like, a whole new level of importance. We're not just talking about accuracy here. We're talking about interacting with, like, delicate biological systems.
Absolutely. When we talk about actuation in biomedicine, we need systems that can operate at incredibly small scale, so micro or even nano, while applying minimal force to avoid damaging any cells or tissues.
So it's like performing surgery with the touch of a feather.
Yeah, that's a great analogy. And on top of that, biocompatibility is essential. So the materials used in these actuators, they need to be compatible with the human body. They can't trigger any adverse reactions. Ideally, they should also be non-invasive or at least minimally invasive to reduce the risk of complications.
Okay, that's a tall order. So which of our actuation all-stars are, like, up to the challenge of working in this, like, delicate environment?
Let's revisit 6 of them, I think, and explore how they're being used to create these, groundbreaking biomedical devices. First up, those micromanagers we were talking about earlier, piezoelectric actuators.
Ah, yes, the ones that can flex with electricity. How are they used in medicine?
Well, their incredibly fine control makes them perfect for tasks like manipulating cells, delivering those minute doses of medication with pinpoint accuracy, and even performing some delicate microsurgical procedures.
So they're like the surgeons and pharmacists of the microscopic world.
Exactly. And because they can generate movement without direct contact, they kind of minimize the risk of damaging those delicate tissues, making them ideal for sensitive applications.
That's incredible. What about voice coil actuators? Are they making their mark in biomedicine too?
Oh, absolutely. VCAs are finding their place in medical imaging systems and robotic surgery, where those smooth, precise movements are crucial for navigating those delicate areas within the body. Imagine guiding a catheter through a blood vessel or positioning a probe during an ultrasound.
So they're the precise navigators of the, like, inner body.
That's a great way to put it. And their rapid response times make them well suited for applications where real-time feedback and adjustments are crucial, like in robotic surgery.
It's amazing to think how these technologies are, like, changing the face of medicine. Now, let's zoom in even further and revisit those miniature marvels, electrostatic actuators.
Yes, these tiny actuators are making waves in the world of microfluidics, those tiny, tiny labs on a chip that are revolutionizing diagnostics and drug development. Imagine controlling the flow of fluids through channels thinner than a human hair or manipulating individual cells for research.
It's mind-boggling to think about working at such a minute scale.
It truly is. And because electrostatic actuators are non-invasive, they're ideal for interacting with delicate biological systems without causing harm. They're also incredibly energy efficient, which is a major advantage for, implantable or wearable devices.
Okay, now for something completely different. Soft actuators. What makes them so special?
Soft actuators, these are a real departure from those traditional rigid actuators. They're made from these flexible, biocompatible materials, often polymers, that can mimic the movements of human muscles and tendons. Think of them as artificial muscles.
So they're more like organic extensions of the body than like mechanical devices.
That's a great way to think about it. They're revolutionizing prosthetics and rehabilitation devices, offering a much more natural and comfortable experience for users. Imagine like a prosthetic hand that can gently grasp objects or an exoskeleton that assists with movement in a way that feels, intuitive and natural.
It's like blurring the lines between like technology and biology. But how do they stack up in terms of, precision?
While they might not offer the same level of fine nanoscale control as some other actuators, their strength lies in their compliance and adaptability. They can conform to different shapes, apply those gentle forces, making them ideal for interacting directly with the human body.
It's like having a helping hand that's both strong and sensitive. Now, what about those heavy hitters, hydraulic and pneumatic actuators? They seem a bit, out of place in the delicate world of biomedicine.
You're right, they're not typically used for that direct interaction with cells or tissues. However, they play a really crucial role in like assistive robots and exoskeletons, where their high force output can be harnessed to provide support and assistance for patients with, mobility challenges.
So they're more like the supportive friends, helping us like regain our strength and mobility.
Exactly. They're not about that delicate manipulation, but about providing the power needed to overcome those physical limitations. However, their use in biomedical devices requires careful control and safety measures to prevent any, unintended harm.
Makes sense.
Yeah.
And finally, let's bring back those smooth operator servo motors. Where do they fit into the biomedical picture?
Servo motors are really valuable assets in things like surgical robots and advanced prosthetics where their precision and responsiveness are crucial. Imagine a robotic arm performing those intricate surgical procedures with incredible accuracy, or a prosthetic leg that responds seamlessly to the user's movements.
So they're the steady hands guiding the scalpel and the responsive legs that like keep us moving.
That's a great way to put it. Their ability to provide those smooth, controlled movements makes them ideal for applications where precision and patient comfort are paramount.
It's fascinating to see how all these different actuation systems, each with its own like strengths and limitations, are being tailored to meet the unique challenges of, biomedicine. It's like a toolbox full of specialized tools, each designed for a specific purpose.
And what's even more exciting is that the field's constantly evolving. The development of new materials, miniaturization technologies, those advanced control systems, it's pushing the boundaries of what's possible, leading to even more innovative and effective biomedical devices.
It's incredible to think about the future of biomedicine with these technologies at the forefront. Now, let's dive into one specific type of actuator that's making waves in the world of microdosing medicines. Piezoelectric actuators. We touched on them earlier, but I'm ready to get into the specifics.
Excellent. Piezoelectric actuators are proving to be exceptionally well suited for microdosing applications. They offer that precision and control needed to deliver those tiny, precise doses of medication, often in a targeted and controlled manner.
So we're back to those micromanagers. Remind me what makes them so good at, microdosing.
Well, their ability to generate those incredibly fine movements, right down to the nanometer scale, makes them ideal for controlling the flow of fluids and dispensing those minute quantities of drugs. They're like the master chefs of the pharmaceutical world, carefully measuring out each ingredient for that perfect microdose.
That's a great analogy. So how exactly do they work their microdosing magic? What are some of the methods they use?
Well, there are several fascinating approaches, each with their own advantages. One common method is using piezoelectric micropumps. These tiny pumps utilize vibrating diaphragms powered by those flexing piezoelectric elements to generate pressure waves that precisely control the flow of liquids, delivering medication in those microdoses.
So it's like having a tiny programmable IV drip.
Exactly. Imagine a micropump implanted under the skin that automatically delivers those microdoses of insulin to manage diabetes, eliminating the need for those frequent injections.
That would be a game changer for so many people. What other microdosing methods are there?
Another really clever approach is using piezoelectric microvalves. These tiny valves, again controlled by the precise movements of those piezoelectric actuators, they act like these gatekeepers, regulating the release of minute quantities of medication from a reservoir.
So they're like tiny faucets dispensing just the right amount of medication on demand.
That's a great way to think about it. Imagine a microvalve-based inhaler that delivers a precise microdose of asthma medication directly to the lungs when needed. It minimizes side effects and maximizes effectiveness.
These applications sound incredible. Are there even more ways piezoelectric actuators are being used for microdosing?
There are. We're just getting started. Let's talk more about them in part 2 of this deep dive.
Okay, I can't wait. So I think we've covered a lot of ground for now, from the basics of actuation to the intricate world of piezoelectric microdosing. Join us in part 2 as we continue our exploration of these fascinating technologies.
See you there. Welcome back to our exploration of precision actuation. As promised, let's delve a bit deeper into this world of piezoelectric microdosing. It's all about precision and control at that microscopic level, which is just so crucial for targeted drug delivery.
Yeah, last time we were talking about micropumps and microvalves, those tiny marvels that precisely control the flow and release of medication. I'm eager to learn more about those other piezoelectric microdosing methods. What else is out there?
Well, there are a couple of really fascinating techniques that I think you're going to love. One that comes to mind is piezoelectrically driven microneedles.
Microneedles. Now, those sound a bit intimidating.
I understand where you're coming from, but they're actually designed to be much less invasive and painless than traditional hypodermic needles. So these tiny needles, they're coated with medication, and with the help of those piezoelectric actuators, they gently vibrate into the skin.
So instead of like a sharp jab, it's more of a gentle buzz.
Exactly. The vibrations help the microneedles painlessly penetrate that skin barrier, creating these tiny channels for the medication to be released in a controlled manner.
That's pretty amazing. It's like these microneedles are like carefully weaving the medicine into the skin. What kind of medications are like best suited for this type of delivery?
Well, microneedles are showing some great promise for delivering a wide range of medications, actually, including vaccines, hormones, even pain relievers. Imagine a microneedle patch that continuously delivers a vaccine over, an extended period, eliminating the need for those dreaded booster shots.
That'll be a game changer,
Yeah.
especially for people who are needle phobic. Are there any other applications for this technology that you're kind of excited about?
One that I find particularly intriguing is using microneedles for personalized skincare. Imagine a microneedle patch with those, customized ingredients that target specific skin concerns, delivering them directly to those deeper layers of the skin.
Whoa. So instead of slathering on like creams and hoping for the best, you could get like targeted treatment directly where it's needed.
Exactly.
That's a beauty revolution waiting to happen.
Yeah, it is.
Now, what about that other microdosing method you mentioned, piezoelectric inkjet printing?
Oh, piezoelectric inkjet printing. This is another fantastic example of how, precision engineering is revolutionizing medicine. It allows for the precise deposition of tiny droplets of medication onto a substrate or directly onto the skin.
So it's like a microscopic inkjet printer that prints with like medicine instead of ink.
That's a great way to think about it. And what makes this technique so powerful is its ability to create those customized dosage forms.
So instead of those mass-produced pills, we could have like personalized medication printed on demand.
Exactly. Imagine printing microdoses of medication onto these, edible films that dissolve in the mouth. This would be a game changer for children or anyone who has difficulty swallowing pills.
It's like turning medicine into candy. Now, that's what I call a spoonful of sugar to help the medicine go down.
Hmm.
Are there any other innovative applications for piezoelectric inkjet printing in medicine?
Definitely. Imagine printing personalized skincare treatments, catered to specific skin conditions, or even printing medications directly onto bandages for wound healing.
It sounds like piezoelectric inkjet printing could like open up a whole new world of possibilities in personalized medicine.
It really could.
And finally, we have the last method on our list, piezoelectrically assisted drug release from nanoparticles. This one sounds particularly futuristic.
Oh, this approach is really cool. It involves encapsulating medication within, tiny nanoparticles. They act like these miniature delivery vehicles. And here's the kicker. Using piezoelectric vibrations or electric fields, we can trigger these nanoparticles to release their contents at a specific time or location within the body.
So it's like sending in a fleet of like micro drones, each carrying a payload of medicine, and then like activating them on command to release their cargo exactly where it's needed.
You got it. Imagine nanoparticles carrying a chemotherapy drug that are injected into a tumor. Then, piezoelectric actuators trigger the release of the drug directly at that tumor site, minimizing damage to those surrounding healthy tissues.
That level of like targeted treatment is incredible.
Yeah.
It's like turning science fiction into reality.
It really is a remarkable feat of engineering. But as with any new technology, there are, challenges to overcome. Safety is paramount, and rigorous testing is crucial to ensure these systems are delivering the right dose at the right time. We also need to ensure biocompatibility to prevent any, adverse reactions within the body.
Those are some important considerations. It sounds like researchers and engineers still have some work to do to bring some of these applications to fruition. What other hurdles do they face in developing and implementing these piezoelectric microdosing systems?
Well, one ongoing challenge is finding reliable and long-lasting power sources for implantable or wearable microdosing devices. We need batteries that are small, safe, and can provide power for extended periods without needing to be replaced.
That makes sense. I can only imagine how tricky it must be to power these tiny devices.
It certainly is. And then, of course, there's the cost factor. Developing and manufacturing these advanced technologies can be expensive, which, can initially limit their accessibility to patients who need them.
It's always a balancing act between, innovation and affordability.
Mm-hmm.
But with continued research and development, I'm hopeful that these groundbreaking technologies will become more readily available.
I agree. The potential benefits are immense. More precise drug delivery, reduced side effects, personalized treatment, targeted therapies. It's revolutionary.
It really does paint a picture of a future where medicine is more personalized and effective. Now, before we move on, I want to go back to our source material, the checklist on microdosing extruders.
Yeah.
So I talked about, those broad applications of piezoelectrics in microdosing, but this checklist seems laser focused on using these systems for a very specific purpose, extruding powders.
You're right. And that makes sense because a lot of medications, even materials for implants, they start out in powder form. So extruding these powders with precision is a key step in creating those microdosing systems, particularly for things like transdermal patches or those tiny implantable devices we were talking about.
So it's like taking the raw ingredients and then like shaping them into the precise forms needed for microdosing.
Exactly. Think of it as like a microscopic 3D printer, but instead of using, plastic filaments, it uses those fine powders to build these complex structures for delivering medication.
That's a great analogy, but I imagine powders can be like tricky to work with. What factors determine which powders are like suitable for piezoelectric extrusion?
You've hit on a key point. It's not a one-size-fits-all approach. Particle size and flowability are crucial. Piezoelectric actuators, they generally work best with fine powders that flow easily and can be precisely controlled by those tiny movements of the actuator.
So it's like finding the right consistency of dough for baking.
Yeah.
Too crumbly and it won't hold its shape. Too sticky and it won't flow through the piping bag.
Perfect analogy. If the powder is too coarse or clumpy, it can, clog up the system. And if it's too fine, it might not extrude smoothly or could even become airborne.
So finding the Goldilocks powder is key. What about the powder's properties? Do those matter too?
Absolutely. One important property is that the powder's what we call viscoelasticity. This refers to its ability to both stretch and return to its original shape. It's like stretching a rubber band. It deforms under stress, but snaps back when you release it. Powders exhibit this behavior too, and it influences how well they respond to those vibrations of the piezoelectric actuator during extrusion.
So you need a powder that's got that perfect balance of firmness and flexibility.
Right.
Anything else to consider?
Well, density and granularity also come into play. Denser powders might require more force to extrude, potentially exceeding the capabilities of a piezoelectric actuator alone.
It's like trying to push a heavy object versus a light one. It takes more effort.
Exactly. And if the powder is too granular or coarse, its large particle size, it might not respond well to those fine movements of the piezoelectric actuator,
Wow.
leading to uneven or inaccurate extrusion.
So there's a lot of like science and engineering involved in finding the right powder for the job.
There is. But thankfully, there's a whole world of powders out there, each with those, unique properties and applications just waiting to be explored.
Okay, I'm ready to dive into this powder paradise. Let's start with something familiar, polymeric powders. What are they and why are they a good fit for piezoelectric extrusion?
Polymer powders are essentially tiny plastic particles. Think of materials like polyethylene, the stuff, plastic bags are made of, or polylactic acid, which is a biodegradable plastic that's often used in 3D printing.
So we're talking about like everyday plastics just in a powdered form.
Exactly. And what makes them great for piezoelectric extrusion is that many polymers naturally flow well and respond predictably to the actuator's vibrations. They're like the building blocks of the microworld.
So it's not just about medication delivery. We can use piezoelectric extrusion to shape all sorts of like tiny plastic components.
You got it. From microfluidic channels to tiny gears for micro robots. The possibilities are vast. Now, let's move on to something a bit more high-tech: ceramic powders.
Ceramic powders. I usually associate ceramics with like delicate teacups and bathroom tiles, not high-tech applications.
I understand the association, but ceramics actually encompass a much wider range of materials than just, tableware. Think about alumina, which
Yeah.
is used in high-strength components, or zirconia, which you find in dental implants.
So ceramics are a lot more versatile than I realized.
Yeah. Absolutely. And when these materials are ground into those fine powders, they open up a whole new world of possibilities. We can use piezoelectric actuators to precisely extrude these powders, creating these intricate and durable components for everything from electronics to biomedical implants.
It's amazing how a material as seemingly simple as ceramic can be used in such like cutting-edge applications.
It really is. Now let's shift gears to a material that's essential for many industries: metal powders.
Metal powders. I imagine something like heavy and industrial, not something you'd, you know, manipulate with these tiny actuators.
Metal powders might, conjure up images of heavy machinery, but they can be surprisingly fine and delicate. Think about a titanium powder used in aerospace applications, or stainless steel powder for medical implants.
So even metals can be tamed into these fine powders.
Precisely. And these metal powders are revolutionizing manufacturing through a process called metal additive manufacturing, or more commonly 3D printing with metals. Piezoelectric actuators play a vital role in this, enabling the precise deposition of metal powders to build those complex components layer by microscopic layer.
Wow. 3D printing with metal. That sounds incredibly futuristic. Are there any challenges in using piezoelectric actuators to extrude metal powders?
Yeah, metal powders can be quite dense, which means they sometimes require more force to extrude than some other materials, and this can kind of push the limits of what a piezoelectric actuator can handle on its own.
So sometimes those tiny actuators need a little extra help to handle the heavy lifting.
That's right. But engineers have found clever ways to integrate piezoelectric actuators with other systems, like pressure-assisted extruders, to overcome that limitation.
It's fascinating how even at the microscopic level, teamwork is essential. Now let's talk about a type of powder that's particularly relevant to our discussion of microdosing: pharmaceutical powders.
Ah, yes. Pharmaceutical powders. These are the building blocks of many medications. Think about the active pharmaceutical ingredients in, those pills and capsules, or the excipients, those inactive ingredients that help deliver the medicine effectively.
So those familiar capsules and tablets, they all start out as powders.
In many cases, yes. And this is where piezoelectric actuators really shine. Their precision and control are ideal for handling these sensitive powders, ensuring that each dose contains the exact amount of medication needed.
So they're like the master pharmacist, carefully measuring and dispensing those
Yep.
those active ingredients to create those life-saving medications.
That's a great way to put it. And because many pharmaceutical powders are fine and free-flowing, they're well suited for piezoelectric extrusion, allowing for the creation of those sophisticated microdosing systems we discussed earlier.
It's amazing to see how these tiny actuators are contributing to such like important advancements in medicine.
They truly are. Now, for something a little different, let's talk about food powders.
Food powders. I'm intrigued.
Think about all those powdered ingredients we use in baking and cooking flour, sugar, spices, cocoa powder, the list goes on.
So we're talking about the building blocks of our favorite treats.
Exactly. And piezoelectric actuators are finding their way into the culinary world too.
Yeah.
They can precisely dispense these powders for applications like automated mixing, portioning ingredients, and even, 3D food printing.
3D food printing. Now that's something I'd love to see in action. Imagine like creating these intricate and customized food designs with the help of piezoelectric actuators. You know, carefully depositing layers of powdered ingredients.
It's a fascinating field that's rapidly evolving, and piezoelectric actuators are playing a key role in making it a reality. Finally, let's journey to the cutting edge of material science, nanomaterial powders.
Nanomaterials. Now we're talking about things that are so small I can barely even imagine them.
Nanomaterials are materials with structures at the nanoscale, meaning they're incredibly small, often consisting of just a few atoms or molecules.
We're talking like manipulating matter at the most like fundamental level.
In a way, yes, and these nanomaterial powders have these extraordinary properties that make them ideal for all sorts of cutting-edge applications, from advanced electronics to targeted drug delivery.
Can you give me some examples of these like super-powered powders?
Yeah, think about carbon nanotubes. These are incredibly strong and lightweight materials that are used in advanced composites, or graphene oxide, a material with these amazing electrical and thermal properties that's finding applications in everything from electronics to energy storage.
So they're like the superheroes of the material world, each
Yeah.
with its own like unique set of powers.
That's a great way to put it. And to harness the full potential of these nanomaterials, we need tools that can manipulate them with incredible precision. That's where piezoelectric actuators come in.
I can only imagine how challenging it must be to work with materials at such a tiny scale.
It definitely presents its own set of challenges. Nanomaterials are prone to, clumping and agglomeration, which can hinder smooth extrusion. It's like trying to squeeze honey through a tiny straw. It takes patience and precision.
I bet. But it sounds like the potential rewards are enormous, with nanomaterials poised to like revolutionize countless industries.
Absolutely. And as our understanding of nanomaterials and our ability to control them at the nanoscale continue to advance, the possibilities just, they seem limitless.
It's truly mind-blowing to think about what the future holds for these tiny materials.
Indeed. Now, with all these, types of powders in mind, let's shift our focus to some of the challenges that are specific to piezoelectric extrusion. Remember how we talked about the importance of, particle size, flowability, and those other properties that make a powder suitable for this process.
I do. It sounds like finding the perfect powder is a bit like Goldilocks trying different bowls of porridge. It has to be just right.
That's a great way to put it. Sometimes even when you have a powder with the right properties, there can still be, challenges during extrusion.
What kind of challenges?
Well, one common problem is powder cohesion. Some powders tend to stick together, forming these, clumps that can disrupt that smooth flow and clog this extrusion nozzle.
So it's like trying to extrude a clump of wet sand. It just won't cooperate.
Exactly. And this cohesive behavior can be influenced by factors like humidity, temperature, even the electrostatic charge of the powder particles.
So it's not just about the powder itself, but also about the environment it's in.
Precisely. Another challenge can arise from the powder's density. Dense powders require, more force to extrude, which can sometimes exceed the capabilities of a piezoelectric actuator alone.
It's like those tiny actuators are hitting the gym, trying to push those heavy powders through the nozzle.
That's a great way to visualize it. And if the powder is too granular, meaning it has, large particles, those particles might not respond well to the fine movements of the piezoelectric actuator, leading to an uneven or inaccurate flow.
So there's a delicate dance between like the powder's properties and the actuator's capabilities.
Absolutely. But thankfully, engineers have developed some clever solutions to overcome these challenges. One approach is to use vibration-assisted feeding mechanisms that help break up those clumps and ensure a smoother flow of powder.
It's like giving the powder a little shake to loosen it up before it goes to the extruder.
Exactly. Another strategy is to pre-process the powder to reduce its cohesion, either by modifying its surface properties or adding these, special flow enhancing agents.
So it's like prepping the powder for its big performance,
Yeah.
making sure it's in top shape to glide through that extruder.
That's a great way to think about it. And these pre-processing techniques can make a world of difference in achieving that smooth and precise extrusion.
It's fascinating to see how much thought and engineering goes into optimizing this seemingly simple process of pushing powder through a tiny nozzle.
It truly is a testament to human ingenuity. By understanding the nuances of those different powder types and developing strategies to overcome those challenges, we're unlocking the full potential of piezoelectric extrusion.
And this brings us back to the bigger picture of microdosing. By mastering the art of powder extrusion, we're creating the building blocks for those innovative drug delivery systems that are revolutionizing medicine.
That's right. And that's what makes this deep dive so exciting. We're exploring not just the technical details of actuation and powder extrusion, but the profound impact these technologies are having on healthcare and beyond.
It's like a journey from the microscopic world of actuators and powders to the macroscopic world of human health and well-being.
Precisely. And speaking of journeys, I think we've reached a good stopping point for this part of our exploration. We've covered a lot of ground, from the principles of microdosing to the fascinating world of powders and the challenges of piezoelectric extrusion.
This has been an incredible journey. I'm already eager to hear what's next.
Join us for part 3, where we'll wrap up our deep dive with some final thoughts and reflections on this amazing world of precision actuation and its impact on our lives.
Welcome back to the deep dive.
Yeah.
We've been on this incredible journey, exploring this whole world of precision actuation systems.
Yeah, it has been quite a journey, from those mechanics of tiny movements to their impact on, things like biomedicine and microdosing.
I feel like I've gained a whole new perspective on these invisible forces that are literally shaping our world,
Yeah.
especially those operating at those mind-bogglingly small scales.
And the thing is, we're really just scratching the surface of what these, technologies can actually do.
Yeah.
I mean, as our understanding of material science and engineering just keeps advancing, the possibilities seem limitless.
I can't help but imagine a future where tiny robots are delivering personalized medicine to individual cells, or where 3D printed organs are being created with just incredible precision. It sounds like science fiction, but with these advancements, it feels like we're getting closer to that reality every day.
I agree. Those visions aren't as far-fetched as they might seem. We're living in an era of just extraordinary technological progress, and precision actuation is right at the heart of it.
It's both exciting and humbling, to think about the impact these technologies will have on our lives. But before we get too lost in the future, let's take a moment to kind of reflect on what we've learned. We've covered a lot of ground, from those fundamental principles of actuation to the intricacies of microdosing and powder extrusion.
Yeah, we explored this diverse array of actuation systems, each with its own unique, strengths and applications, and we saw how piezoelectric actuators in particular are playing this really pivotal role in shaping the future of medicine, offering the potential for more targeted, personalized, and effective treatments.
And I'm especially fascinated by those those microdosing methods that we discussed, like the micro pumps, the micro valves, and those incredible microneedles.
Oh yeah.
It's amazing how engineers are harnessing these tiny movements to create those innovative drug delivery systems.
It's really a testament to human ingenuity, finding ways to control and manipulate matter at such a minute scale. And it's not just about, medicine.
Right.
We've seen how precision actuation is being applied in fields ranging from robotics to manufacturing to even, food production.
That's right. From From 3D printing with metal to creating customized food designs, the applications they seem endless.
It's been a journey that's highlighted not only the remarkable ingenuity of human engineering, but also the profound impact it can have on our lives.
One of the biggest takeaways for me is that precision isn't just about, accuracy. It's about control, refinement, and constantly pushing the boundaries of what's possible.
Yeah.
And it's clear that precision actuation is a key enabler in this quest for ever greater control over the physical world.
Exactly. It's about harnessing the power of those tiny movements to create these significant impacts, whether that's, guiding a surgical robot with incredible accuracy or delivering a life-saving medication in a targeted microdose.
Well said. So as we wrap up this deep dive, what final thought would you like to leave our listener with? What's the one thing you hope they take away from this exploration?
I would encourage our listener to just stay curious, and keep exploring those possibilities that precision actuation, offers. This is a field that's constantly evolving with new discoveries and innovations emerging all the time. Who knows what groundbreaking advancements await us just around the corner.
I think that's the perfect note to end on. A sense of wonder and a thirst for knowledge are the best tools we have for navigating this ever-changing technological landscape. Thank you for joining us on this incredible deep dive into the world of precision actuation. We hope you've enjoyed the journey and come away with a newfound appreciation for the tiny forces that shape our world. Until next time, keep those minds curious and those imaginations engaged.